Okay, so in this lecture, we are gonna discuss about automorphisms. Okay, so the very basic definition of an automorphism is an isomorphism from a group onto itself. Okay, so let me just give the definition. So let G be a group. Let G be a group. An isomorphism. An isomorphism from G onto itself is called an automorphism. Is called an automorphism. Okay, we denote we denote the set of all automorphisms on a group G by AUTG. Yep. Okay. Okay. So let us straight away start with a proposition which helps us understand the concept of automorphisms better. First of all, let us first also observe this. So this is an observation that if you take any bijective mapping, let us suppose F1 is a mapping from G to G, F2 is again a mapping from G to G, both are bijective. Okay, then F1 composed with A2 is also a mapping from G to G, right? And it's again bijective. This is very basic properties of bijective functions. Moreover, if F1 and F2 both are homomorphisms, then F1 composed with F2 is again a homomorphism. So the set automorphisms on G, this forms a group under composition function, right? So it forms a group under composition of functions, forms a group. Clear? Okay. Now what we try to do is that we try to bring together the concept of a group action and an automorphism, right? So let's declare it as a proposition. So let H be a normal subgroup of G. Okay. Then G acts by conjugation. G acting on H by conjugation is an automorphism on H. Clear? Clear? So what are we actually trying to say here? So let me just explain this. That is, so G acts on H such that any element H you take, it gets mapped to GHG inverse via the mapping sigma G. So if you remember, then sigma G was called the associated permutation representation afforded by an action, right? Right. So this defines an automorphism on H. Clear? Clear? Further, what can we say more? Further, the associated permutation representation afforded by this action on on H. So this is a homomorphism from G into the set of all automorphisms of H, having kernel the centralizer of the elements in H. We are having the kernel as the centralizer of the elements in H. Clear? So that is, we can further extend this as saying that G mod the centralizer of the elements in H is isomorphic to a subgroup of automorphisms of H. A subgroup of the set of all automorphisms of H. Clear? Okay, let me go to a new page. Okay, wait a second. Yeah. Okay, so wait a sec. Yeah. Okay. So let us come to the proof of the statement we had. Okay. Okay. So proof. Let me do it with this color. Yeah. So what are we saying is basically that you have a group G. It acts on H, where H is normal in G, right? H is normal in G, and the action is such that the action of G on H is G H G inverse. Okay. So let sigma G be the mapping from H to H such that sigma G of an element H is mapped to G H G inverse. Okay. Now is this a 1-1 mapping? Okay. So this is trivially a 1-1 mapping by the left and right cancellation laws, right? See, this function is obviously well defined because since G is a normal subgroup of G, since H is a normal subgroup of G, therefore every element of this form is in H, right? That is the definition of a normal subgroup. Clear? So this mapping is obviously well defined. Further, if you have sigma G of some H1 equal to sigma G of some H2, then that implies GH1 G inverse is equals to GH2 G inverse, and this means H1 is equals to H2, right? By left and right cancellation, I'm not writing that. And it being an onto mapping is pretty trivial because for every element GH G inverse you have, for all GH G inverse in H, there exists an element small h in H such that H is mapped to GH G inverse, right? So, no, this is pretty trivially an onto mapping. So it's a 1-1 mapping, it's an onto mapping. Sigma G is a bijective mapping. Clear? You can also you could also show this directly by showing there exists some sigma G inverse, an inverse mapping of this mapping you have. Further, is this a homomorphism? So if you have sigma G of H1 H2, then this can be written as, so this is G H1 H2 G inverse, but you can write it as G H1, between H1 and H2 you can put G inverse G H2 G inverse, and then by associativity this becomes GH1 G inverse times GH2 G inverse, right? So this is sigma GH1 and this is sigma GH2, right? So this defines an automorphism, right? By definition. Now if you consider the homomorphism, or you might say if you consider this mapping psi from G to A to H, such that any element G is mapped to sigma G, then you can obviously show that this is a well-defined homomorphism. Because suppose you have phi of G1, G2, psi of G1, G2, then this becomes sigma G1, G2 of some H, right? So this happens for all H in capital H. So this is equals to, so G1, G2, H, and G1, G2 whole inverse, right? So that is G2 inverse, G1 inverse. But this can be written as G1, G2, H, G2 inverse, G1 inverse, right? So this is obviously sigma G1 composed with sigma G2 for all H, right? Therefore, it's a homomorphism. Therefore, psi is a homomorphism. Now, what can you say about the kernel of this? So, what is the kernel of psi? So, kernel of psi is set of all elements small g in capital G such that psi of G is the identity mapping. Right? So, it's the identity mapping. So, G in G such that psi of G is nothing but sigma G of H, which is equals to identity, right? So this happens for all H in capital H. So obviously this means that, so it maps, so basically this mapping has H mapped to H, right? So we can write it as identity of H, right? So basically this maps G H G inverse to H for all small h in capital H, right? So this is the other way of saying that it has those elements which commute with the element H for all H in H. Therefore, we can say that this is the set of all elements which commutes with the whole set capital H. So we can write it as the centralizer of capital H. Right? So we know that by the first isomorphism theorem what happens. So by the first isomorphism theorem we know, by first isomorphism theorem we know that G mod kernel of the mapping psi must be isomorphic to the image of this mapping psi, right? So this implies that G mod centralizer of H is isomorphic to, and this is obviously a subgroup of the automorphism set, right? So this is a subgroup of AUPH. Clear? Yeah. Okay. Yeah. Okay. So now let us proceed towards some corollaries related to this concept, this proposition I might. So the corollary. So the first corollary let's speak about. We say that if K is any subgroup of G and we choose an element small g from capital G, then K is isomorphic to the set, or you can say to the group GKG inverse. Okay. And if so happens, then we can also extend this corollary by saying that conjugate elements and conjugate subgroups, right? Conjugate elements and conjugate subgroups have same order. Now the second part of the proposition is pretty trivial, right? There is nothing much to say about it because you have a well-defined isomorphism. The first part of the statement is also very easy to notice because in the proposition we proved, if you consider H is equals to G, right? Then you have G acting on G by conjugation, right? By conjugation. Then you have sigma G of A as G inverse for all small a in G. So if you restrict this, so that implies we can say that sigma G of A is equals to G inverse for all A in some subgroup K, right? But Obviously this is again a homomorphism, right? So this is again a, so since sigma g is a homomorphism in G, sigma g is again a homomorphism when it is restricted to K, right? So it being a 1-1 mapping is also pretty trivial. To ensure that it's an onto mapping, we can just restrict sigma g as the mapping from K to G K G inverse, right? Then this definition of sigma g just shows that K is isomorphic to this, right? Clear? Clear. Okay. Let's proceed to the next part. Okay. We have one more proposition to, sorry, one more, I should say, one more corollary to follow. The corollary says that for any subgroup H of G, the normalizer of H in G mod the centralizer of H in G is isomorphic to a subgroup of the automorphisms of H. Clear? In particular, G mod the center of G is isomorphic to a subgroup of the automorphisms of G. Okay. So how do we prove this? Now notice that H is normal in the normalizer of H, right? Therefore, the proposition we proved, if the complete proposition is stated again by just replacing G with the normalizer of H in G, then the same statement holds, right? There is nothing different. So since H is normal in the normalizer of G, by the action of the normalizer of H on H by conjugacy, we can state this, right? So NGH divided by CGH is isomorphic to a subgroup of the automorphisms of H. The next part is again very trivially noticed, because if you consider H to be G, okay, if you consider H to be G in the previous proposition, then the normalizer of G in G is G, or you can just extend this, okay, and the centralizer of G in G is the center of G, right? So that implies G mod the center of G is isomorphic to a subgroup of the automorphisms of G, right? Clear? So this automorphism defined by the action of conjugacy is called an inner automorphism. Definition. So let G be a group. So let G be a group, and let the small g be in capital G. Then conjugation by G is called an inner automorphism. Is called an inner automorphism. And the set of all inner automorphisms of G is denoted as INN G. Clear? Clear? Thus, therefore, by the previous proposition, now obviously notice that let us just move back to the proposition we had. See, I'm just giving you the hint of it. So by the previous proposition, let me just explain this a bit. So what I'm trying to say is that, so what did you have in the proposition? You had a mapping G to the set of all automorphisms of H, right? Right. So you can also replace this by G, because you can consider the action of G on itself. But if you, but not considering the whole of automorphisms of G, if you just consider the automorphisms of automorphisms inside the inner automorphism set, then this becomes an onto mapping, right? Then this becomes an onto mapping by definition of the action of conjugacy, right? So this becomes an onto mapping. So by the previous proposition, we can say that G mod ZG, that is this one, is isomorphic to the inner automorphisms of G, right? And this very important to know. Clear? Okay. Now let us understand a few examples regarding this. Example number 1. Suppose G is abelian. Suppose G is abelian. Then sigma G of H is GHG inverse, but this is equals to H, right? Therefore, this is the trivial action. Therefore, this is the trivial action, right? Is the converse true? The converse is typically true, right? Converse gives you the definition. Simple. So, therefore, we can say that G is abelian if and only if sigma G is trivial. Sigma G, wherever I write sigma G, it means the associated permutation representation afforded by the action of conjugacy. Clear? Okay. Now, let us consider example number 2. Okay. So, suppose you consider the group Q8. So, what is the center of Q8? Center of Q8 is 1, right? So, this for all n greater than or equal to 3 we are considering. Okay. So, now what are the number of elements in Q8? So, we have 8 elements. The center consists only one element. Sorry, it can be generated by 1, right? Yeah, it can be generated by 1, correct. It consists of 2 elements, basically. So, therefore, we can say that so in Q8, or I can directly say that the inner automorphism of Q8, so this is isomorphic to the Klein 4 group K4, yeah, correct. Klein 4 group. Okay. Similarly, if you consider Sn for n greater than or equal to 3, then what are the number of elements in Sn? So this is 1, right? This is 1, right? What are the number of elements in Sn? So Sn, you have n factorial elements. Then Sn mod Zn, Z of Sn. This is isomorphic to Sn itself, right? And this is indeed isomorphic to the inner automorphisms of Sn. Clear? Okay. So these are a few typical examples. Okay. Now, one more example we should consider. It is that suppose you take H to be isomorphic to Z2. Okay. So this can be thought of an observation. Okay. Suppose H is isomorphic to Z2. Okay. Then we know that Z2 has unique elements of order 1 and 2. Now, since Z2 has unique elements of order 1 and 2, so that implies H has unique elements of order 1 and 2, right? But suppose now we consider the automorphism which H can opt. Okay. So what can be the automorphism? Now suppose H is of this form. So it is of the form 1 and A, where A is of order 2 and 1 is trivially of order 1. Then the only possible automorphism is mapping 1 to the identity. I mean mapping 1 to 1 and mapping A to A, right, in H. The reason being because you can't map A to 1, right? Because then the order won't be preserved. While automorphisms are all isomorphisms, right? Under isomorphisms, the orders of elements are preserved, right? Right? So you can't map A to 1, nor can you map 1 to A. Therefore, the only possible automorphism is the identity automorphism, right? Right. So if so, then we can say that the normalizer of H in G must be equal to the centralizer of H in G. Okay. So therefore, if H is normal in G, then that would imply H is contained in the center of G, right? So this is also a very important observation. Clear? Okay. Now let us straight away come to a certain propositions. The main goal of this of this of this lecture, you might say, is to prove certain facts about certain finite groups. Okay. We want to show that goal we want to show that if G is a group of order PQ such that both are primes and P does not divide Q minus 1, then both are primes, P is less than equal to Q and P does not divide Q minus 1, then G is abelian. So this is the first thing which we want to prove. And the second thing which we want to prove is that if G is a group of order PQ such that P is not equal to Q and both are primes, then G is a cyclic group. Okay, these two things we want to prove now. Okay, so let us first prove a few basic things. So yeah, so definition. Okay, a subgroup H of G is called characteristic in G. Denoted as H char G if every automorphism on G maps H to itself. That is sigma of H is equal to H for all sigma in the set of all automorphisms in G. Clear? Okay. So certain very evident observations from here is that if K is a characteristic in H and H is normal in G, then that implies K must be normal in G. And the second observation is that if H normal in G is unique of some given order, then H is characteristic in G. H is characteristic in G. Clear? Okay. So let's move on to a proposition. The proposition says that the automorphism group of a cyclic group, the automorphism group of a cyclic group of order n is isomorphic to Z mod nz star and abelian group of order phi. So Z mod nz star basically consists of those elements, those natural numbers, or I should say those whole numbers from 0 to n which are co-prime to n. So Z mod nz star, it consists of those natural numbers, let's say. So those natural numbers such that a is less than n and a mod, so the GCD of a and n is 1. So this is pretty trivially noticed that, so the order of such a group must be phi, because it determines the number of elements co-prime to it, right? Okay. So let's prove this. Proof. Okay. Now, what we do is that we know that if you have a cyclic group of order n, then that is isomorphic to Zn, right? So we prove this statement for Zn itself. So let Zn be generated by the element x. Okay. If this mapping psi belongs to the automorphism group of Zn, then psi of x must be some x to the power a, right? For some a in Z, because every element in Zn is of the form x to the power a, right? We are actually considering the multiplicative form of writing, nothing else. Clear? And also, and a uniquely determines n, right? Unity determines phi, sorry, psi, because this is an automorphism, so it's a 1-1 mapping, right? Therefore, let this mapping be denoted as psi. Clear? Now order of x is n as order of Zn is n. Therefore, a is defined modulo n, right? Modulo n. And since psi a is an automorphism, x and x to the power a has same order, right? Has same order. So by the order properties, we know that then the exponent a and the order of x, that is n, they must be co-prime. They must be co-prime. So what we have shown, basically, we have shown that if you consider any automorphism psi, then with respect to psi we can produce an integer a, or typically we can produce an element x to the power a in Z mod nz, Z mod nz star, right? Because these exponents a are all modulo n. Now conversely, if a is an integer co-prime to n, then x getting mapped to x to the power a is again is an automorphism. Is an automorphism on Zn, automorphism of Zn. Therefore, psi from automorphism of Zn to Z mod nz star defined as psi of a is getting mapped to a modulo n is, so it's an isomorphism. It's an isomorphism. Alright, the other issue is surjective. It's surjective. Right? It is surjective, and this is injective by definition, right? This is injective by definition. Now, what is psi a composed with psi b of x? So this is x to the power ab, right? But x to the power ab is nothing but psi ab of x. Right? Therefore, this mapping psi of psi ab is nothing but psi a composed with psi b. So it's a homomorphism as well. It's a homomorphism. And uniqueness, that is the 1-1 mapping, that's evident from how this mapping psi a is constructed basically, right? So psi is injective evidently. So you can just work it out. It's very easy to notice. Therefore, automorphisms of Zn is isomorphic to Z mod and Z star. Clear? Okay. Now let us come to the next proposition. Next proposition. Proposition. Let G be a group of order PQ such that P and Q are primes with P less than equal to Q and P not dividing Q minus 1. Then G is abelian. Then G is abelian. Okay? Okay. Yeah. Now P and Q can be same as well. If P and Q are same, then the order of G is P squared, right? And we have already proved that a group of order P squared is abelian. So that's a, in this case, that's a trivial statement. So we don't need to consider them to be same. That won't make a difference, to be very honest, in this proof at least. So how can we proceed? Notice that if the center of G is not equal to 1, then that means, by the Lagrange's theorem, the center of G can have the values P or Q. The order of center of G can have the values P or Q. So that means G mod ZG can have the order P or Q while both are primes. While both are primes. Right? So that implies G mod ZG is cyclic. But that means G is abelian. So it's a very important proposition regarding quotient groups of center of a group. Let's prove this statement first. Okay, let's prove this statement first. So how do we prove this statement? So suppose, let me change the color. Suppose G mod ZG is cyclic. Then let G mod ZG be generated by the element X ZG, where X is in G. Clear? Therefore, for all G in G, the element GZG can be written as some x to the power m ZG, or I should rather write it like this. So this it's x ZG whole to the power m, but that is by definition x to the power m ZG, right? Right. But that means x to the power minus m. So if we are pre-multiplying by x to the power minus m, G ZG is equal to ZG. And we know by the properties of cosets that mean that x to the power minus mg is in ZG, right? Right. Therefore, there exists an element small z in ZG such that x to the power minus mg is equals to z, but that means g is equals to x to the power m. Clear? Now suppose you choose two elements from G. Therefore, let G1, G2 be in G such that G1 is written as x to the power m1 z1 and G2 is written as x to the power m2 z2. Then what is G1, G2? So G1, G2 is x to the power m1 z1 x to the power m2 z2. But z1 and z2 are elements from the center, so they commute with every other element in G, right? And x to the power m1, x to the power m2, these are elements from G. So z1 will commute with x to the power m2, right? So this becomes x to the power m1, x to the power m2, z1, z2. That is equals to x to the power m1 plus m2, z1, z2. This is equals to x to the power m2 plus m1, z1, z2, right? Now, so we can write it as x to the power m2 times x to the power m1, z1, z2. Now z1 and z2 commute with each other because they are elements from the center. So this can be done as x to the power m1, z2, z1. So now z2 again commutes with x to the power m1 because z2 is an element from the center. So it is x to the power m2, z2, x to the power m1, z1. But x to the power m2 is nothing but g2. And this is x to the power m1, z1 is g1. So it is equal to g1. So g1, g2 is equals to, therefore we have g1, g2, but did I consider those elements? Yeah. So g1, g2 is equals to g2, g1. Since g1 and g2 were chosen arbitrarily, so the group G is abelian, right? Yeah. So we will use this fact. Okay. We will use this fact in this. Okay. So proof. So let ZG be equal to 1. Clear? Then, if every non-identity element of G has order P, if every non-identity element of G has order P, then the centralizer of every non-identity element has index Q, right? Then the centralizer of every non-identity element has index Q. Therefore, the class equation of G is, so the order of G is PQ, the order of the center is 1, and so suppose we have K number of centralizers, so you have KQ, right? So this is why from the class equation. Clear? But Q divides PQ and KQ, but Q does not divide 1, right? Therefore we have a contradiction, right? Therefore a contradiction. So contradiction, so that implies there exists a non-identity element. There exists a non-identity element of order Q. Clear? Say the element is X. Say X. Then suppose we consider the subgroup generated by X. Then the order of H is Q because the order of X is Q. So what is the index of H? So that implies the index of H in G is P, right? But we know that the order of G is PQ and P is less than equal to Q. So P is the least or the minimal prime which divides G, right? Since P is the minimal prime dividing G, we know that if P is the minimal prime dividing the order of some group G, and there exists a subgroup of G which has index P, then that subgroup is normal in G, right? Then H is normal in G, right? Then what is the centralizer of H? So centralizer of H is H, right? Right. And the normalizer of H is the whole group G, right? Therefore, G mod H, which can be written as the normalizer of H in G mod the centralizer of H in G. So this is a group of order P. This is a group of order P, right? It's a group of order P, and it is isomorphic to a subgroup of automorphism of H, right? This we have proved in the first proposition. Sorry, I guess in the corollary. Yeah, corollary of the first proposition, which is isomorphic to a subgroup of automorphisms of G, automorphisms of H, sorry, automorphisms of H. But we proved in the previous proposition that the automorphism of H, that the order of the automorphism of H must be psi of Q, that is equal to Q minus 1, right? Therefore, by Lagrange's theorem, P must divide Q minus 1, but that's a contradiction because we are told that P does not divide Q minus 1, but that is a contradiction. That is a contradiction, right? So that's a contradiction. So if it's a contradiction, then that means that Zg, mod of Zg is greater than 1, but that means that G mod Zg is cyclic. That means G is P. Clear? Clear? So the other proposition which I just stated before coming into these proofs was that if the order of G is PQ such that P and Q are primes and P is not equal to Q, then G is cyclic. I don't have much time to prove this now, but if I just give a hint of this thing, that use the Cauchy theorem. The Cauchy theorem says that if G is a finite group and a prime P divides the order of G, then there exists an element small g in capital G such that the order of G is prime. That very prime. So if the order of G is PQ, then you can choose an element from G such that the order of X is small p. You can also choose an element from G such that order of Y is Q. Then check what is the order of XY. Okay, and try to prove that the order of XY is PQ. If you prove this, then you can obviously say that G is generated by XY, because the order of XY is PQ and the order of G is also PQ, and then you will have your proof. Okay, so meet you guys in the next lecture.